Imagine you are an autonomous vehicle navigating a dense urban center. You're a defense analyst tracking a sudden border deployment, or a public health official modeling a fast-moving disease outbreak. But suddenly, an unmapped event occurs. A water main breaks, completely blocking a critical arterial intersection. If you open up a standard commercial large language model, ChatGPT, and ask it how to reroute your assets to avoid that block, it will give you a beautifully formatted, highly confident response. The pros will be flawless. The logic on the surface will sound completely convincing. But if you take that generated route and plot it on a real map, you might find a catastrophic problem. The AI might tell you to drive straight through a solid concrete retaining wall. It might tell you to cross a massive river at a point where no bridge has ever existed. Or it might suggest a path that quite literally violates the fundamental laws of gravity and terrain elevation. Why does this happen? It's not because the model lacks data. It's because the AI doesn't know where it actually is. It doesn't possess a mental map. It has absolutely zero structural understanding of physical reality. While Google Maps occasionally makes headlines for navigational errors, its failures are edge case anomalies, whereas the ungrounded mistakes of an LLM would be catastrophic and systematic by design. There's a lot of hype around AI these days. You see big promises and headlines, and vendors claiming their software can solve your hardest problems tomorrow. But when you get past the marketing, the real world looks very different. The world is messy and complicated. Protecting national funds, fixing old infrastructure, or tracking public health takes real effort. The data isn't neat, and the stakes are very high. Most of those slick, one-size-fits-all AI solutions just don't hold up when faced with tough, unpredictable reality most organizations deal with every day. We must face the reality that our world is an incredibly diverse and complicated system. Even the foundational pioneers of modern artificial intelligence have realized that we're reaching a ceiling with large language models. Yann LeCun, a pioneer in the field, founded AMI Labs, raising over $1 billion in capital with an explicit goal to pivot away from purely text-based language models. LeCun's core argument is simple. A single-minded focus on autoregressive models, glorified next word prediction engines, is not the end-all solution. Because these models only predict words, they can't understand the physical world, the why. Because the physical world is continuous, high-dimensional, and governed by the basic laws of physics, none of which can be truly understood by simply predicting the next token in a sentence. We are seeing this massive shift play out right now across the world's most advanced AI labs. Recently, NVIDIA released Cosmos 3, explicitly marketing it not as a chatbot, but as an omnimodal for physical AI. They built a modular mix-and-match AI structure designed to ingest sensor data, predict future world states, and simulate physics before acting. When the biggest hardware and AI company on Earth pivots from text generation to building physics-grounded world simulators, you know the paradigm has shifted. This shift opens the door to something even more fundamental: the power of data fusion. I believe that integrating vastly different types of data, from satellite imagery to real-time sensor arrays to demographic and economic data, is the only way to solve our most critical and complex problems. We are entering an era in which AI must do more than just process the language. It must ingest, harmonize, and synthesize diverse multimodal inputs. As AI capabilities will advance, we will inevitably invent new sensors to acquire data we can't even imagine today. To truly understand our world, AI must be built to handle that complexity, not by ignoring it, but by embracing the messy, multi-layered reality of our physical environment, our world. I'm Scott Pesanowski. I've spent the last 25 years navigating the friction point between what technology promises on a slide deck and what actually works in our dynamic world. My PhD is in AI and informatics. I have an interdisciplinary background, so I'm dedicated to being a bridge, translating complex, high-level geospatial data into production-grade architectures that executives and domain experts can actually defend and trust. In this video, we're going to pull back the curtain and expose the massive, hidden geospatial blind spot lurking inside generative AI. We will break down exactly why large language models are fundamentally ill-suited to compute distance and topology, relationships, spatial relationships, how my past research in geospatial natural language processing sought to bridge this linguistic gap, and how a hot phenomenon called physics-informed world models will completely disrupt the geospatial industry. Make sure you stick around until the very end of this video, because I'm going to share a major strategic shift happening right now at labs like Google and World Labs. It's a shift that will fundamentally redefine how we build private, secure, and sovereign Earth intelligence. If you are ready to see how we build these private, production-grade intelligence that survives the real world, let's get to work. Let's start by considering the core problem. To understand why generative AI struggles so deeply with physical reality, we have to contrast how a language model views a map and how a geographer views a map. If you ask an LLM right now to give you the exact driving distance between New York City and Los Angeles, it will spit out an answer instantly. If you ask it which state sits directly west of Arizona, it will answer correctly. Because of this flawless performance on basic geographic trivia, the average user and even many technology executives make a massive logical leap. They assume that because the model can describe space, it must understand space. But it doesn't. It only understands language. To an LLM, the word London, New York, or Kuwait is not a physical place anchored to the surface of the Earth. It is a token. It's just a number, or more accurately, it's a set of numbers in a giant filing system optimized to predict which words belong together. The AI groups words together based on patterns it has seen before. It's not looking at a map. It's looking at a massive complex spreadsheet of word associations. The model knows that the token London is highly likely to appear in a sentence next to Big Ben, Heathrow, the River Thames. The model has memorized millions of text strings about geography, but it lacks the fundamental rules of how maps are actually drawn, measured, and calculated. It understands our world entirely semantically, not geometrically or topologically. This deficiency becomes glaringly obvious the moment you push an LLM outside of its training data and force it to engage in complex, multi-step geospatial reasoning or physical constraint tracking. Think of a simple physics experiment. If you tell an LLM there was a wooden block sitting in the center of a flat table. If I tilt that table 45 degrees to the left, what happens to the block? The model does not open up an internal physics engine to calculate the forces at play, such as mass, friction, and gravity. Instead, it scans its neural network to predict the most statistically likely next words based on descriptions of tables and blocks that it has read on the internet. If you slightly alter the prompt to include unusual material or complex geometry that wasn't heavily represented in its training data, the linguistic illusion we're seeing breaks down. The model cannot simulate gravity. It cannot compute friction. Now, contrast that probabilistic text generation with traditional geographic information systems, geospatial databases, or network topologies, what are commonly used in routing. If you ask a standard geospatial routing engine to find the optimal path for a logistics fleet, it doesn't take a shot at the answer based on vocabulary trends or word co-occurrences. It executes precise, math-based logic over a network graph. It knows the exact coordinate boundaries of every polygon. It understands containment, whether point A sits inside or outside zone B. It computes adjacency, road segments that share a physical intersection. It operates within a rigid framework of mathematical truth. The great danger of the current AI hype cycle is that enterprise organizations are actively trying to force these purely linguistic engines to perform highly deterministic geospatial and operational work. They are treating text predictions as decision-making engines for the physical world. Let's be clear about the stakes here. When a chatbot hallucinates a fake historical fact or inserts a non-existent citation into a college essay, it's annoying. It's a minor blemish on the technology. But when an enterprise AI confidently hallucinates geospatial reasoning while routing a global supply chain, deploying emergency medical personnel during a crisis, or simulating the localized impacts of a changing climate, it is an absolute disaster. You cannot build a resilient, defensible future on a generic algorithm that lacks the deep, scientific context of the physical world. But as an industry, we need to realize that this friction point, this tension between the fluid, messy nature of human language and the rigid, absolute geometry of the map is not a new problem. In fact, some of my earliest academic research over a decade ago focused on addressing this exact vulnerability. We were trying to figure out, how do you build a verifiable understanding between the words humans speak and the coordinates the Earth demands? Long before large language models became a commercial sensation, we were trying to decipher what we called geospatial natural language processing, or geospatial NLP, and the concept of geoparsing. We were trying to teach computers to read maps, and geoparsing is the process of turning human spoken phrases of written text, like near the old market, into exact pinpoint GPS coordinates on a digital map. Some simple examples are when London is mentioned in the same context as someone saying they were driving to Toronto, knowing that person meant London, Canada, not London, England. Or when I say I'm looking forward to visiting Happy Valley, it means I am going to State College, Pennsylvania. Throughout my time as a research professor at Penn State University, I worked on this precise vulnerability. We architected and deployed a suite of open source research frameworks specifically engineered to bridge the fluid human expressions with the rigid coordinate geometry. Our approach addressed every dimension of the pipeline. We designed scalable enterprise search engines like GeoText to automatically extract place mentions from unstructured text. We built GeoCorpora to tackle the massive training data problem by teaching machines what real-world locations actually look like. And we layered on analytics frameworks like SensePlace and GeoCam, which allowed human experts to visualize, verify, and map those insights, even deciphering messy, spoken directions into hard coordinates. Our goal back then was to establish a rigorous link between unstructured text data, like digital news feeds, humanitarian reports, and public microblogs, to actual coordinate geometry on the surface of Earth. We quickly ran into a huge challenge that today's AI developers are completely glossing over. The problem of implicit geography. Humans simply do not communicate like a database. When a crisis hits, or when an operational event occurs on the ground, people don't broadcast their location in latitude and longitude. They don't use normalized address points. Instead, they say things like, just past the old market, right next to the flooded bridge, or 3 miles south of downtown. If a city planner, a public health director, or an emergency responder was to use textual data to save lives during an unfolding disaster, a machine has to do a massive amount of heavy lifting. It has to ingest the messy text, isolate the place names, figure out which exact physical location on Earth is being referred to, resolve massive coordinate ambiguities like determining which of the dozens of cities named Springfield someone means, and then plot that onto a map. In my dissertation research, I called it geomovement. I pushed these boundaries even further. I wasn't just looking for static place names anymore. I built specialized model pipelines to extract descriptions of human movement and geospatial impediments directly out of unstructured text. If a local newspaper or a field report mentioned that a mystery fever was moving along a specific transit corridor, or that a heavy rainy season had blocked a particular mud road, my system had to parse those linguistics. I architected these systems to extract co-occurring locations, enabling us to map potential disease transmission networks. I learned very quickly that if you try to do this with a loose probabilistic model, it fails miserably. It lacks the administrative and scientific rigor for high-stakes operational environments. True geospatial intelligence requires that anchoring to official, authoritative, verified map databases, coordinate reference systems, and rigid geospatial rules. We often take for granted that tracking assets such as ships, delivery trucks, or even tagged wildlife is a solved problem because we have high-precision GPS. But that technical luxury vanishes in the scenario of high-stakes law enforcement when tracking illegal activities like drug trade routes or movement of endangered wildlife. There's no clean GPS feed. You are left with a fragmented, messy mosaic of intercepted text messages, phone call transcripts, and dark web chatter. My work was designed to bridge the gap, taking the fragmented noise and extracting geospatial intelligence needed to map out threats. The modern generative AI hype cycle is trying to convince the enterprise world that we can completely bypass these types of scientific research. Software vendors are telling organizations that they can just take their raw, unstructured text, feed it into a massive public language model, and magically get back accurate geospatial reasoning. It looks incredibly impressive in a slick surface demo. The chatbot will read a document and confidently summarize a geographic path for you. But because it is still operating purely on token probabilities, it lacks an explicit audit trail. It lacks a defensible architecture. It is predicting the next word, not calculating the landscape's actual geospatial constraints. So how do we fix this right now? If you're an executive or technical leader operating in our complex reality and need to leverage the incredible linguistic power of modern models without inherently their catastrophic geospatial blindness, what is the blueprint? The answer lies in a highly secure, data-grounded architecture known as sovereign geospatial RAG. Sovereign simply means your data stays behind your own firewall, under your complete control, and never leaves your secure digital walls to train a public model. The current blueprint for fixing the geospatial limitations of large language models isn't to wait around for someone to build a trillion parameter general model. It is to implement a highly targeted engineering pattern known as geospatial retrieval augmented generation, or geospatial RAG. Just to be clear, you cannot fix a language model's fundamental geospatial blindness by simply shoving more text down its throat. Instead, you have to construct an explicit, secure data pipeline that wires the linguistic intelligence of the model, the LLM, directly into verified geospatial knowledge graphs, enterprise geographic databases, and specialized geospatial foundation models, which are AI models built specifically for geography. Think of it as transforming the AI from an overconfident student guessing answers from memory into an analytical expert taking an open book exam where the textbook is a precise, highly structured GIS database. When I look at complex operational environments, such as the predictive disease forecasting we're building at the WHO, this is exactly how we could enforce data integrity. We wouldn't allow a language model to guess where an outbreak might emerge based on historical text patterns in training data. Instead, we could architect the system as a coordinator. It can ingest unstructured data feeds, filter them through a strict place, time, concept mechanism, and anchor that text against real-time satellite data, such as rainfall totals and vegetation health, to ensure every output is grounded in verifiable physical measurements. Earlier, I mentioned the challenge of geoparsing, and I architected a framework called the Onslaught API that demonstrates this RAG pattern perfectly. It first uses NLP to extract place mentions from text, which NLP can do really quite well. Then it tasks an LLM with identifying London, Ontario, Canada from the text using context, the context around the words. But the model doesn't then infer coordinates. Instead, it passes that place name to a standard geocoder, which performs a lookup against an authoritative database of verified locations to return the precise ground truth coordinates. This is the essence of geospatial RAG, leveraging the large language model's linguistic extraction power, what it's really good at, but grounding the final geospatial output in the rigid, verified truth of a map database. More importantly, for organizations managing critical infrastructure, national defense assets, or sensitive corporate operations, this entire pipeline cannot exist in the public cloud. It must be entirely sovereign. If you are a national bank, a regional health director, or a major utility provider, you are legally forbidden from piping your proprietary infrastructure maps, logistic pipelines, or localized facility logs into a public commercial API black box. To build for true sovereignty, you can pull highly capable open-weight models like ZAI's GML models securely behind your institutional firewall. You then fine-tune that model on your highly localized geography or business context. But you don't stop there. You use the fine-tuned model as an intelligent semantic router, connecting it directly via secure interfaces to your secure, organized data systems. When you build a sovereign geospatial RAG system, you create a dual engine architecture. The language model handles the natural language interface, interpreting exactly what an executive or a field team is looking for. But the geospatial database handles the math. It matches the writer's intent with the geometric precision of a coordinate reference system. This method is the exact integration pattern that moves AI out of the realm of speculative hype and into defensible science. It creates a comprehensive audit trail. If a model highlights a sudden operational risk or flags an anomaly, a human operator can pull back that curtain and see the exact geospatial queries, temporal filters, and data inputs that generated that conclusion. But as powerful and necessary as geospatial RAG is for modern enterprise workflows, we have to be honest about its limitations. It is still a text predictor querying a static tabular database. It is a dramatic improvement, but is not the final destination. The true disruption, the shift that might completely upend how we understand geographic systems, urban planning, and physical risk over the next 10 years, lies in a radical new class of AI that bypasses databases entirely. We are moving past static maps and entering a new phase, the world model. This brings us to the frontier of artificial intelligence. While large language models are fundamentally designed to predict the next token in a sequence, a true world model is designed to learn the statistical structure of space and time. It is an AI built to learn an internal predictive simulation of physical reality itself. It learns how light falls on a surface, how terrain grades, and how physical objects respond to force. These models aren't a fringe concept. Some of the biggest names in AI are betting the future on it. Yann LeCun recently founded AMI Labs, raising over $1 billion to pivot away from text explicitly. LeCun argues that single-minded focus on LLMs is reaching an end because real-world data is chaotic, unbroken stream of geospatial and temporal variables. To truly get to where we want to, we need action-conditioned world models that learn causality and geospatial dynamics by training on video and geospatial sensor data rather than just text. But as this technology explodes, a massive rift is forming in the industry. It is a divide that every technology executive, urban planner, and geospatial professional needs to understand now. It is the divide between renderers and simulators, or I guess you'd say the Hollywood physics versus reality. Right now, companies are capturing massive headlines by showing off AI that can generate rich, interactive 3D environments from a single prompt. These models are incredible feats of engineering, don't get me wrong, but they are primarily optimized for visual perception. They operate on Hollywood physics. They are generating CGI, not engineering. If you prompt a visual world model to simulate a flash flood hitting a dense city block, it will generate a stunning video in which the water appears to flow correctly. But looking real is not the same as being real. A visual render does not compute actual hydrologic pressure. It is not calculating terrain roughness, mass conservation, or gravity. If you are trying to deploy emergency medical resources, protect a fragile supply chain, or reinforce a critical railway embankment, a visual, pretty 3D animation is dangerously misleading. It falls into the exact same trap as the fake digital twins I've criticized in the past. It's just a sleek 3D movie set. Real digital systems must stay in sync with reality and support decisions as conditions change. When lives and structure are on the line, you don't need a cinematic approximation. You need a deterministic calculation. The future of our industry belongs to physics-informed world models. Instead of the AI guessing how the world behaves based on pixels, we hard-code the fundamental laws of nature, like how gravity pulls things down, how water flows downhill, and how objects react when they bump into each other, directly into the model's structure. Fei Li's team at World Labs recently published a taxonomy that draws a hard line between models that merely output pixels for human eyes and true simulators that respect Newton's laws and maintain geometrically faithful representations of reality. Meanwhile, Google's Neural GCM is drawing attention by creating hybrid atmospheric models that simulate large-scale planetary dynamics using traditional physical laws, while leveraging machine learning to simulate small-scale, chaotic phenomena. When you apply these physics-informed constraints to geography, the entire paradigm changes. We are moving toward a reality where physics engines, models that understand exactly how nature works, will merge with maps. These models know exactly where pipes, roads, and buildings are located on Earth, and how those pipes could behave during a natural disaster. When those two forces collide, the traditional geospatial workflow will be completely unrecognizable. We have covered a lot today. We discussed how general-purpose language models suffer from a fundamental geospatial blind spot, how we can use sovereign geospatial RAG to ground them, and how the rise of physics-informed world models will redefine future physical simulation. The ultimate takeaway I want you to get out of this is, if your organization is managing real assets, tracking real diseases, or planning real infrastructure in the physical world, you cannot rely on AI models that only understand words, or for that matter, even other AI models that understand only one type of data. You need architectures that respect physical constraints, protect data sovereignty, and deliver defensible, transparent science. Moving from static geospatial databases to dynamic, physics-aware world models is a massive shift. It is simply too much to cover in the final minutes of this video. That is why my entire next video will be a dedicated deep dive breakdown focused solely on the mechanics, frameworks, and enterprise applications of geospatial world models. We will look at how to build AI architectures that not only look like the Earth, but also physically think like the Earth. If you want to make sure you don't miss that deep dive, hit the subscribe button right now. And if your team is currently navigating the integration of unstructured data, LLMs, and geospatial pipelines, let's connect. Drop a comment below. What is the biggest roadblock you are facing right now when trying to make your AI models actually understand physical reality? You can also reach out to me directly via the contact links in the description below on my website. Let's build the future of secure, sovereign Earth intelligence together. I'm Scott Pezinowski. Thanks for watching, and I'll see you in the next one.